Okay, today we start Chapter 3. So Section 3.1, we're going to talk about functions and function notation. So what we'll be doing in this section is that we're going to be analyzing relationships. So first, let's define a relationship. We call that a relation. So definition, a relation is a set of ordered pairs. Remember, ordered pairs are x's and y's. Okay. So what do I mean by that? Well, a set, we can use our set notation. So let's say, for example, we have the ordered pair 1, 2, and then the ordered pair 2, 4, and the ordered pair 3, 6, and the ordered pair 4, 8, and 5, 10. Okay? So this is a relation. It's a set of 1, 2, 3, 4, 5 ordered pairs. Okay. So the domain is the first component. In the ordered pair. So it is usually denoted by the letter x. We also talk about it as being the input of the function. We also talk about it as being the independent variable. Then we also have something called the range. And in a relation, that's the second component. We usually let that be denoted by the letter y. We also talk about that as being the output of the function or the dependent variable. Now with this, we can also do mappings. So let's say we have one group of numbers, and this is the domain. Say there's some element in here, we'll call it p, whatever. Once we put it through a function, it will map to another place m, okay, another component m. If we're using our x and y terms, some x would go to some y. We could also have another element in here, we could call it r. Okay. And it's okay, r could go to m. Sometimes you'll see me do something like this, another mapping, p, x, r. Okay, this would be the domain. And this would be the range. Some m and some y. Another way to map this is, well, p goes to m, x goes to y, and r also went to m. So this relationship, this is the range. Okay. So this relationship is a function. And we'll define what a function is in a minute. Let me just give you some more mappings. Here's another mapping. We could have p, q's, and r's being our domain. If p goes to x, this would be the range. Then q could go to y, and let's say r goes to z. Okay. This mapping is also a function. Here's another. Let's say in the domain there's P and Q, and that P goes to X, and that Q goes to two separate values, Y and Z. Now this is not a function. So let's define what a function is. Okay, so by definition, a function is a relation in which each possible input value or value of the independent variable so that is the domain elements, leads to exactly one output variable, one output value, or one value of the dependent variable. So in this case, we have that. Here are our values of the independent variable, and they go to exactly one value of the dependent. We also have that in this case. While both P and R go to M, P only goes to M, and R only goes to M. So for each value in the domain, it goes to only one value in the range. This case, it's not true. Okay? So this value of the domain only goes to 1x, but this value of to one value in the range, okay, which we've just called x here. But this value q is going to both y and to z. Okay, so this is not a function. So let's look at like menu values, okay? Say for example we were given this. Okay? Here's our menu. Okay. Does this represent a function? And if so, is it a function of what? Okay. So we have plain donuts costing $1.49, jelly costing $1.99, and the chocolate also costs $1.99. Well, we could do our mapping here. We're wondering about is the price a function of the item, or is the item a function of price? Okay, so if we look at this, we have the plain, we have the jelly, and we have the chocolate. So the plain maps to $1.49, and the jelly maps to $1.99, and the chocolate maps to $1.99. So in this case, this mapping does represent a function, and we'll say this is the domain and this is the range. So the price here is a function of the item. Okay? The independent variable is the item. We'll do some more examples of finding this. let's also talk about function notation. So this function of notation. So definition 4, we have function notation. And that is written like this. Okay? This means, this is read, f of x. Okay? It is a function of x. Okay? This does not mean f times x. So for example, if we have the number of days in a month, we could use we could use function notation to represent the function whose input is the name of the month, and then what would come out would be our range values, and it is the number of days in that month. Okay, so if the output is the range, that's what's coming out. Okay, so those are the days, and that is a function of the input, and the input is the month. So in this way, a specific example would be, for example, 31 is a function of, now in this case, January. This is our output, okay, so the range. This is the rule that we're applying, and this is our input. Okay, this is an element from the domain. Okay, so that's in general what a function is. Now let's start looking at some algebraic functions. So for example, if we had f of x, okay, this is our function, and it is defined as x squared plus 3x minus 4, we can evaluate this at various values. For example, we could say, let's evaluate it to. So how that happens is that instead of evaluating the function at x, I want to evaluate it at 2. Okay. And that's equal to, now our function says, whatever's inside of here, we're going to square it, plus 3 times whatever's inside of here, minus 4. And what we've decided to evaluate at is 2. And now we can just simplify this. 2 squared is 4. 3 times 2 is 6. Minus 4 is equal to 6. We could do a change of variables also. Instead of evaluating our function at x, we could evaluate it at a. We'd read that f of a. But the form will stay the same. Whatever's inside of here gets squared, plus 3 times whatever's inside of there, minus 4. And in this case, we're just multiplying, or we're evaluating at a. And so at this one, it just looks like a squared plus 3a minus 4. It's just a change of variables from here to here. We could evaluate at more than just one variable, we could evaluate at the sum. Let's say a plus h. But again, the structure stays the same. We take whatever's inside of here, we're going to square it, add 3 times what's inside of there, and then subtract 4. So this is the setup. Now this can be simplified. Okay. Remember that this means a plus h times a plus h. Okay. And from here we could distribute this through. So we get 3a plus 3a plus 3h, and then subtract 4. Now, let's expand this. By foiling, what we'll get is a squared plus ah plus another ah. Remember, ha and ah are the same thing because addition or multiplication commutes, plus h squared. And then we'll just copy the rest from above. Then lastly, what we'd want to do is combine like terms. Okay. And in that case, AH and AH, if I add those together, I'm going to get 2AH. And the rest will just come along because they're not like terms. So in that way, we see that f of a plus h is equal to this. Okay, and we can make it a little more complex. Let's say we wanted to take f of a plus h and then subtract off f of a. We can also then divide by h. So let's see if we can find this entire quantity. Now, we found parts of these all together. F of a plus h we just found, so this is equal to a squared plus 2ah plus h squared plus 3a plus 3h minus 4. Just from our previous example. Now, from the formula we want to subtract f of a, okay, and f of a we found here to be this. Now this is a polynomial, so remember when you're subtracting polynomials, you're going to need to distribute the negative across. So let's put up the parentheses. This is a squared plus 3a minus 4. And then all of this is still just divided by h. Okay. So we saw that this can't be combined. We're going to try and simplify now. So we'll just copy f of a plus h. But we have to remember to distribute this negative. And then a negative and a negative become positive. The denominator is already simplified, so we'll just copy it as well. Now we can see that some canceling will occur. If we have a squared and we subtract off a squared, that will cancel. If we have positive 3a and we subtract off 3a, that will cancel. And negative 4 plus 4 will also cancel. So what we're left with is 2ah plus h squared plus 3h. And all of that is divided by h. And now I see that there's an h in all of these, so I could split this up is the first term over h plus the second term, h squared over h, plus the third term, 3h over h. And then we can see the h's will cancel. I'll be left with one h up top here, and those will cancel. So in the end, there's just 2a plus the h over 1, which is just h, plus 3. So make sure you really understand how to do this example and how to find quantities f of a plus h minus f of a over h. This is an important topic for us. Now we can also solve functions graphically, equations graphically. So let's say, for example, that I have h of p, okay, so that says the independent variable here are the p's, is equal to p squared plus 2p. Now let's solve where our function is equal to 3. So the important thing to note here is that if this is the function h of p, and we want to know where h of p equals 3, well, you just take that function and you set it equal to 3. And now this is just a simple quadratic that we can solve. This is p squared plus 2p minus 3 equals 0. This will factor. We need a p and a p plus 3 minus 1. Then using the zero product property, it's either that p plus 3 equals 0 or p minus 1 equals 0. So p is equal to negative 3 or p is equal to positive 1. So this is solving algebraically. Means put your pencil to the paper and do the algebra. However, let's say I was given a graph and it looked like so. This would be some function. Okay, let's say this is h of p. Okay. Now these represent the x, and these represent the y's. Remember, the y's are also the function values of x. Okay, f, y, and f of x play the same role. Okay. What I would be looking for then, if this is h of p, and I want to solve where h of p equals 3, then this is the line y is equal to 3. Which I could put in. So this is the horizontal line, y is equal to 3. And if I'm wondering where these two graphs are equal without having the function to solve, what I would have to do is look for intersection points. And these intersection points would lead to the solution. Okay. And it turns out this is the point negative 3, comma 3, and this is the point 1, comma 3. If you were actually to graph these. And so what we can see then is that the x values of the coordinates are the solutions to this equation. Where is it that h of p is equal to 3? Well, that's when p is equal to negative 3, because p is playing the role of x, okay, and 1. And this is known as solving graphically. We graph the left-hand side of the equation, h of p, and then we graph the right-hand side, 3, and we look for intersection points. That is solving graphically. Let's say we have an equation 2n plus 6p is equal to 12. Okay, so this is an equation that we have. It expresses a relationship. And now I want to write this where p is equal to some function of n, if this is possible. So the way we're going to go about doing this is that we need to solve for p, and if what's left over is only n's and constants on the other side, we will have succeeded. Okay. So let's solve this for p. We need to subtract 2n from both sides. And now I haven't quite solved for p. P is being multiplied by 6, so let's divide everything by 6. Then here the 6's will cancel, and we have p. Here also, 6 goes into 12 2 times. And here we also have some canceling. 2 goes into itself once and into 6 3 times. So we have minus n over 3. It's important to note that this is the same thing as 2 minus 1/3 of n. Right? Because if we put this over 1 when we multiply them back together, we get n over 3. So now we've succeeded. This is a function in terms of n, okay? Because there's only n's, coefficients, and constants on this side. Let's try another one. Let's talk about circles as functions. Okay. So the basic equation for a circle is x squared plus y squared is equal to r squared. Okay. All circles that are centered at the origin can be written this way. So let's look at our basic one, where what we call a unit circle, where the radius is 1. Then we would have x squared plus y squared is equal to 1. Let's try and write this so that we have y is equal to some function of x, if possible. So to do that, we need to solve for y. So we'll have y squared is equal to 1, and I'm subtracting x squared from both sides. Now, when we do this, we have y squared is equal to 1 minus x squared. Y is not solved for yet, so we'll need to take the square root of both sides to undo this squaring. So we'll have y is equal to, now be careful here, don't forget the plus or minus the square root of 1 minus x squared. So the question becomes, is this actually a function? That is, if I put in one value of x, will I get a single value for y? Okay. And from the plus or minus, if you put in a value for x, you can evaluate this, but then you're going to get y is equal to plus that value or y is equal to minus that value. So this is actually not a function of x. What you can do, however, is you could split this up, and you could think about this as, well, y is equal to the positive of 1 minus x squared. Now this is a function. Or if you look at the negative branch, this is a function, if you just take them one at a time. Turns out this is the top half of the circle, and this is the bottom half of the circle. And if you look at those parts separately, they will be functions. But we'll come back to this. Alright. So let's try and do a few things here. And let's say that I have this graph. Okay? So I don't know what this function is, but we are given this. Now, if, for example, I want to find f of 2, well, I need to find then what value does the function take on. Remember, these are the function values when x is 2. So when x is 2, I come up here and the function value is 1. So f of 2 must equal 1. If I wanted to find f of 3, I would come over to 3 and find the function value at 3, and that function value is 4. Now conversely, if I want to find where the function equals 4, okay, that would be the line y equals, so I would need to put that in, that horizontal line. Sorry, I don't know what was going on there with that. So this is a line y equals 4, and I need to find the intersection points. And I can see that that occurs at 2 different places, there and there. Okay. So here, once, so a solution to that is x is equal to -1. But it also would intersect here at x equals 3. Let's try a different one. Well, here you can specifically see it a little bit better, where they put in the line y equals 4. Okay, and let's do one more like that. Now, if this is our function, okay, let's solve where f of x equals 1. Well, if this is where it equals 4, here's the line y equals 1. There's 2 different spots, when x is 0 and when x is 2. Okay, so the value x equals 0 and x equals 2 solves this equation. And notice I didn't have to know what the function was in order to solve that, provided I was given the graph. So let's say we have 3 different graphs in front of us. One looks like this. And let's say one looks like this. Let's call this one f of x. We could call this one g of x. Well, actually we don't, we'll get there. And then over here, let's do our circle. Okay. I've written this as a function. I'm saying this is a function. I've written this as a function. Notice I've not written this as a function. We decided earlier that a function, that a circle was not a function. So the question is, why could I just write that as a function of x? We have a handy tool to help us. Remember that a function, for each independent variable value, there will only be one function value. Okay, so x and f of x. And the helpful test for that is the vertical line. So let's say I pick any value of x, say here. If I draw a vertical line, this graph, the vertical line will only cut this graph once. So for whatever value of x this is, there was only one output function value. Also, if I did it over here, the vertical line would only intersect once. Okay? So for this input value of x, there's only one function value. And I could do this for the rest of them, and they would only cut once. Okay, remember, these arrows are indicating that they're going off to infinity. Okay. So by the vertical line test, I can say, yes, this is a function. And notice with this one I said it was a function as well, because if I do the vertical line test again, testing for the relationship, okay, I only have one intersection point. So for each input value, there is only one output. So yes, this is a function. Okay. So it passes our vertical line test. Now here with the circle, if I use the vertical line test, okay, we can see that this is not a function. It fails our vertical line test. So that's a quick way to determine about graphically whether something's a function or not. There's another type of function that is important to us. That is a one-to-one function. So a one-to-one function first of all, it has to be a function. Is a function in which each output, okay, so now we're talking about the range, corresponds to exactly one input. That is from the domain. So let's go back and look at our mappings that we had before. So from here, this isn't even a function, so it's not going to be one-to-one. What about here? Now remember, to be one-to-one, we look at the range first of all, and we're wondering if this was our output, what got me there? So in this case, if I'm at Z, it's very clear that I came from R. And if I'm at Y, it's very clear I came from Q. And if I'm at X, it's very clear I came to P. So this also happens to be one-to-one. Now the other one we'd said was a function was here. So I start with the range. And here at M, well, let's start with this one. With Y, it's very clear that if I came from Y, or if I'm at Y, I came from X. But with M, I'm not so sure. Did I start with R, or did I start with P? This is not clear. So this is not one-to-one. One-to-one. And luckily we have a test for that as well. Okay. Let's look again at our functions. Okay, so the two graphs that we were just looking at that were functions were this and this one. These were the basic shapes. We called this one f of x. We said this one was g of x. So the question is, are these one-to-one? So now, when we're looking for this, we want to start with the range. Okay. So these values. And I'm asking myself, do I have only one x value that corresponds? And in this case, here's the x value, here's the x value, here's the x value. Here's x, here's x, here's x. Okay. So this is a one-to-one function. Okay. That is, it passes now not the vertical, but the horizontal line test. Let's try that over on F. Up here I'm okay, it'll only cross once. And there I'm okay. But here we get a problem. For this value of the function, there are 3 different x values that have come in. And so I do not know, if I start at this function value, which of these I came from. So this fails the horizontal line test. And so it is not one-to-one. All right. Also in this section, I'm going to be posting a worksheet for you. These are our basic toolkit functions, and I'm going to be asking you all sorts of questions about them. You will need to work through that worksheet. It's also part of the, you will need to work through it and get to know these functions by heart. If you're having some problems with it in the book, I will have to find what page it's on. It will walk you through doing this. And they begin on page, okay, so our toolkit functions. Your book calls them toolkit functions. Sometimes I call them basic functions. Also another word for that is the parent functions. And page 246 is where you'd like to start to help you understand what we're doing. These will need to be committed to memory, but we're going to work with them so much they should just become ingrained as part of who you are. Okay, so that is section 3.1. I will be posting the homework. Let me know if you have any questions.